Okay, so thank you very much for coming. Thank you for Tom and the program committee for inviting me, and I especially appreciate the fact that where we are couldn't be any more convenient for me unless I lived literally in the building. I can almost throw a rock through the window of this building. One of the things that people are advised, or if you ever do any public speaking or presentations, you are sometimes advised to give some sort of physical exercise. I might ask you a question for you to raise your hand and sort of get you engaged, or perhaps I might tell a joke, which would be something I would prefer to do, although a joke for me would be one that's, I like the ones that are stories and that are drawn out, so those of you who may be familiar with the joke. Can you not hear me in the back? Okay, I'll try to speak up a little bit. I think only one of these mics is recording or working. One of the jokes that you may be familiar with that would sort of make you buzz to the idea of a long story is this one called The Aristocrats. Now, I'm not going to do a rendition of that here. I think that would be very inappropriate. But to give you the idea, that's the type of joke I would present. But I must also tell you that I'm kind of operating in the mode of UDP today. And having said that, I don't have time to build up to the joke. I don't have time to do the setup. I also don't, I may have even have told you the joke and you may have missed it. In fact, I wouldn't even know. I may have told it and forgotten that I did, because once I've told it, I've forgotten all about it. And if I told it and you missed it, I'm sorry, because I am UDP and I'm just simply not going to repeat it. I'm not going to retransmit it. So only people in this room, probably within about 100 miles, would even appreciate any part of that joke. And so I've always wanted to actually try to do a version of it. So in any case, I have an argument that or a proposal that I've had for a while that I've wanted to make, is to literally write a book around this notion of how Traceroute can explain the internet. I teach classes at DePaul University, undergrad networking and graduate and networking classes. And I frequently go to Traceroute for all sorts of examples and to describe and explain all sorts of things. I imagine probably all of you have used Traceroute at least once in your career. And you probably have used it recently, and you're probably all very familiar with it. So I'm not going to necessarily go into any detail about how to use Traceroute, but I'm going to try to convey the notion that it can, I think, literally explain just about everything about the internet. So I can't see the slides in here, so you're going to see me looking at the screen. About almost 30 years ago, a gentleman by the name of Van Jacobson had written the very first version of Traceroute. Pushed out an email message, a very brief message, to a couple of email lists. You can see here in what I've included an IETF list. Those of you who've ever participated in the IETF, this is the group that writes the RFCs, the best common practices, literally the standards that we use for all this stuff on the internet. It also was sent to the end-to-end internet interest list, which is a list that also still exists. It's a list where a lot of big ideas in the internet have first been proposed and talked about and discussed. While it isn't as active anymore, you still see some of these frequent contributors from these original days, including Van Jacobson, participate there. I don't know that you can actually find that original code, but you can find code not far from that original piece of code. The one that I had at my disposal was maybe like a year later. And much of the original code actually is not that much different. There's a lot of new features, and of course it's been re-implemented, but there's not much different in the basic idea that Van Jacobson came up with. For those of you who don't know Van Jacobson, by the way, he's an Internet Hall of Famer. He's been literally crucial to the success of the internet in at least a couple of regards. One in particular was it's not an understatement to say he saved the internet from congestion collapse. He contributed to some algorithms in TCP that improved the ability for it to do congestion avoidance, flow control, all that sorts of stuff. And I remember hearing a story at one time early on that he volunteered to rewrite or fix the Microsoft TCP/IP stack because of the problems that it had had and he had already dealt with it. I don't know that he ever was taken up on that offer, but that he could have done that, I think, speaks volumes to his place in the internet. So to describe the process of traceroute that I think we all probably are familiar with, you have this idea where you launch probe packets from a source, which would be this box on the left, and you increment the IP TTL or the IPv6 hop limit field by 1, initializing at 1 for the very first hop. And when you send a packet with a TTL of 1 to towards a destination that's presumably remote, that first router will get that packet, it'll decrement the TTL, and it can't forward it any further because it's now 0. And because of the way we use that field, you can't forward packets that have a value of 0. This is a built-in mechanism into the network protocol that prevents packets from looping forever. Right? All network protocols should have this sort of thing. And so we're sort of living with the misery of this and not having this at layer 2 for some crazy bridge networks, right? But you increment this, and along the way, you get the address of the interface facing the source that's launching these probes. Ultimately, if everything works, you get a response from the destination. Now, you can use or you can create packets with different protocols and ports and so forth to achieve this effect. So in the original design of Traceroute, the one that Van Jacobson had done, he created what we might now call the Unix traceroute, which used UDP probe packets. You would create a UDP message. You would set the destination port to some high-numbered, unlikely used port number on any system, either intermediate gateway or destination host. When this packet is traversing the network and the time to live expires, a router will not be able to respond with UDP, but will issue an ICMP unreachable or time to live TTL expired in response when it does expire. When you get those responses, then that source host starts to build up some insight about the path that it's traversing. When the UDP message reaches the destination, if it does, presumably the destination port is not accessible, there's no service running there, so you'll have a ICMP port unreachable message that will be returned by that destination host. Receiving that will determine whether your trace to the end was successful. So this is Unix traceroute. We all may be reasonably familiar with this process. The other flavor of traceroute that came a little bit later was this idea of using ICMP traceroute. And this was using ICMP echo requests and echo replies. Windows is probably most famous for using this approach. And this works perfectly fine as well. And this may seem a slightly more logical thing to do. And in fact, there's a brief mention by Van sometime after he originally wrote Traceroute, where he explains why he used UDP. And the reason was because early on, some devices simply would not reply with an ICMP error message to ICMP messages. So he had to come up with another way to actually launch the probe packets. But over time, that wasn't a problem, and hosts would be happy to do that, so that ICMP could be used. There is an ICMP option, by the way, for traceroute, but we don't use that by default. Use the ICMP echo request and reply. The only thing, in both cases, but particularly with ICMP, of course, many of you have probably, as you've run this, you will find from time to time that you don't always get responses from either intermediate gateways or the destination host. Is packet filters in the way, or some sort of device. There may be some NAT thing that's happening, so you see strange or unexpected source addresses in reply to your packets. You may even be running your trace route from an RFC 1918 address space, and it will still work. You'll still see the you'll show a few hops with private addresses, but those packets will be translated, and you'll still get presumably a trace route for that public part of that path. But we see things like that happen quite regularly. Now, one of the things that, or one of the few things that Traceroute can highlight are a variety of anomalies. One of those this idea of a multipath. And so I didn't have room to fit everything on the screen so that you could see the full path, but to give you an idea, here's a subset of a trace that I took recently, and you can see in hop 4 and 5, where normally you have 3 responses from the same gateway through a path, we have different responses for each of the 3 probes at those hops. And all that it's implying is there's probably some packet load balancing going there, or some sort of load balancing effect, or the path could be changing, but somehow not all paths are, or not all packets are taking the same path. And so Traceroute can demonstrate and show us this from time to time, and it is highlighted here. Another thing that we might find, and we find this quite a bit now, is some hops will be missing. You run a traceroute, you'll reach the destination ultimately, but somewhere in between you and the destination, some hops will not respond. You'll get the 3 stars, and once, after a few seconds at that interval, once the timeout fires, then you'll try again with a greater TTL, and you'll get past that missing hop, and you'll actually get a response from somewhere further upstream. The typical case might be that this device in the middle may simply not be responding to your traceroute request. Maybe it doesn't respond to ICMP pings. Maybe there's some packet firewall filter in there. Who knows exactly why in every case, but we know, or we can see that this does happen, and it could be something that may be noteworthy. And it may be something we could try to detect or to try to circumvent. So in fact, you might have the case where even the destination is unresponsive. And so this is a trace to Northwestern, a place I've been to school at and have worked at. You can't, by default, at least with the Unix traceroute to Northwestern's homepage. You'll time out after some hop towards that destination. Okay, but we know that destination exists because if you try to pull it up in a web browser, we know we can get there. Well, it's very easy to get around that, because while we're using so-called Unix traceroute, which is using UDP probes expecting ICMP responses, we can try some other type of probe. So I can run traceroute. This is the Linux version with the capital T, and that's a TCP traceroute, and by default that'll use destination port 80. Now that will get me to the destination. As we can see down at the very bottom, that last address is the destination that I'm looking for. And so now I've actually discovered 2 hops, that destination and the one actually preceding it, just by using TCP. So traceroute has helped us overcome some natural limitations based on whatever's going on in the network towards the end there of the path at Northwestern by using TCP over UDP. And then we could talk about, these anomalies. Why do these things happen? Why does UDP not work? Why does TCP work? Why does TCP port 80 work? Why might not UDP port 1900 not work and TCP port 1900 work, and so forth? We could talk about why those things occur simply by demonstrating these sorts of behaviors with traceroute. Another thing that we can see and evaluate is if we were to do a traceroute, in this case to Google, and if we didn't do any special options, we'd see a number of addresses in the path, and we'd see a handful of them all around the same, exhibiting the same response time, roughly, in this case, 20 milliseconds or so. 3 or 4 hops are all about the same response time, round trip time. That might not seem that unusual, but there's clearly a big jump there between 6 and 7, hop 6 and 7. And it seems like perhaps there's some sort of delay between 6 and 7. Something's going on there. Well, if we ran with the MPL or the options, which includes the MPLS options, we might be able to surmise that, well, maybe there's not any actual delay between 6 or 7. It may be that those paths, and I don't know if this is the case here, but it might be, reasonably likely to assume so, that those hops after 6 is just an MPLS path all the way through. And so there's the actual response times that we're getting from traceroute is actually all the way at the end. And the MPLS network is basically doing this ICMP tunneling, which is all of these round trip times are actually being reported from the perspective of that destination that we're tracing to. So that, and I don't know if that's the case here, but I suspect it may be. And Traceroute can help us make at least a better educated guess about that sort of behavior going on, that there's MPLS there, that this sort of behavior may be occurring, helping us better understand how this network is constructed, or at least this path. Now, there's other things that we could do, not with necessarily the default traceroute that you may have, but you can also take your traceroute output and take the IP address and put it through some AS mapping service. Team Cumry, where I work, we're somewhat well known for having this ASN to IP address mapping service. Your traceroutes, there's variants of traceroutes that run through that, so it can show you literally the AS or the network associated with each hop. So it gives you sort of a broader picture of the networks that your path is made up of, as opposed to just simply IP addresses and domain names. Of course, visual traceroute. I don't tend to use this stuff, but you may, but you can get a visual depiction of where packets are going, and this is using geolocation sorts of things, or it could be using ASN mapping types of things. So this stuff exists, so we can talk about how that works at that level, how we can do geolocation with IP addresses. One hack that I thought was clever when I had done it, and someone else had sort of reinvented this later and put it in a proper paper and published it in a conference, was the ability to discover behind any one network, if this network is present at any particular internet exchange, who the peers of that network are. You can do this by using Traceroute. You can identify peering relationships, BGP peering relationships at internet exchanges. If you're behind a particular network and you want to find out who that network peers with others at that exchange, you simply trace to all the addresses within the internet exchange's net block that it's used for peering. So if you're using .1 at the exchange and someone else is using .2, try to trace route to .2 from behind your network. And if you can get to it immediately in one hop, presumably there's a peering relationship. And if not, you may not be able to get there at all, or you may take some other convoluted path, then you can infer that there's no peering relationship. So Traceroute can help you identify literally BGP peering relationships, not something that obviously would have associated with Traceroute, but something you could potentially do. Another one that I had, a few years later I had come up with, I thought was also another interesting hack, is when you look at Traceroute, the output that you get is all the interface addresses facing the source address. So you get that so-called ingress interface towards the source doing the probing. Wouldn't it be nice, or wouldn't it be cool, not necessarily all that useful, but wouldn't it be cool if you could get the IP address of that egress interface along the path? There's no obvious way to do that with Traceroute, but you can in fact do that pretty successfully, and it's really using a brute force method. So rather than, so in addition to doing Traceroute, what you do is once you discover that second hop, so from looking from left to right, that second router, to discover that B address on the first router towards that second one, how do you get that B address? Well, what you do is you first get the A address of the ingress of the second hop router. And you can only assume or presume that the B address preceding it is on literally the same IP subnetwork. It may likely be the next contiguous IP address, one before, one after, but it's probably within the address space, within literally the number line, it's probably close by. So what you do is you simply brute force. You say, well, given the address of A, let me try pinging all the addresses around A. So if A is .1, let me try pinging .2. But I don't just simply ping .2, I set the TTL for that ping to be 1. So it'll never be forwarded by that first router. If that .2 address exists on that router, it'll respond. If not, it won't. So you simply brute force, you do what I call a ring search, and you just look for that address that's within the range of A. And when you get a response, you've discovered it. And this works quite a lot of the time, so it's kind of a neat little hack. So you can discover addresses, then you could maybe narrow in on performance issues and so forth. And I mention this because it's another clever use to do network topology discover and another sort of novel use for traceroute. And so so when we talk about all these things, when we talk about Van Jacobson and the IETF and the internet mailing list, the end-to-end interest list, which is based around this idea of the end-to-end argument, some of you may have heard of. These are things we can talk about just by talking about or using or demonstrating the use of traceroute. We can talk about the history, we can talk about the architectural principles, we can talk about, of course, routing and loops. Sometimes we might see loops with traceroute packets. We can talk about how packets are forwarded or not. We can talk about that hack idea about getting packets to that egress interface so we can discover the full path, both ingress and egress. We can certainly talk about the use of different protocols through the network and how they may be treated differently from others. UDP and ICMP traceroute packets may be filtered, but maybe TCP port 80 packets are not. Why is that? Well, firewalls. Let's talk about firewalls. Let's talk about packet filtering. Maybe we could talk about the domain name system, DNS. When you do traceroute, you're usually doing a traceroute to a name oftentimes, or if you're not specifying otherwise, when you collect all the responses, you're doing pointer lookups. And so you're doing DNS. So we could talk about DNS there. We can talk about the performance. We look at the round trip times. We talk about the geolocation stuff, the ASN mapping stuff, how networks are sort of put together with BGP and all the BGP peering policy stuff. We could talk about header options. We could set source route options, and we can examine ICMP responses because they contain some part of the message that generated that response, that time to live exceeded or whatever the error message is. We can even talk about ARP in some cases, or MPLS, V4 versus V6. Traceroute can bring up all of these issues. We can certainly talk about NAT, and we do, and this is everywhere, and so Traceroute helps identify places where you see private addresses and maybe why you shouldn't see private addresses and maybe why they're not such a good thing in certain cases. You can talk about security issues, router hardening, CPU processing of control plane packets. All this stuff we can talk about. There's a few things that might be a little more difficult to talk about. IP multicast may be a little bit more difficult to talk about in accordance with traceroute concepts, but we might be able to come up with something there. DDoS, we could stretch that. We could talk about DDoS. I could imagine a pretty good DDoS attack using the ideas of traceroute. We won't mention those now while we're on tape, but I think you all could probably imagine some of those. Quality of service, maybe a little bit. PKI, maybe not so much. That may be a real stretch. But then again, if we're talking about BGP and DNSSEC and BGPSEC and RPKI for that environment may come up, but maybe not directly, but maybe indirectly. But all these things, almost everything that we might need to know about how the internet works, I think we can use the example of traceroute to convey many of those ideas. And so this is the thesis of my remarks, and this was sort of the threat I've made to people that if I ever were to write a book about networking, the novel approach to my version of a networking book may be how traceroute explains the internet. So that would be perhaps a useful examination or a useful approach to that. And I'd be interested in your feedback and what other examples of using traceroute to talk about networking and how to understand network and how networks work that you might have that I maybe just didn't include or forgot to mention. So with that, I think we may be just about right on track with time, and so I will conclude just leaving you some references that you may find helpful if you care about traceroute or anything in more detail about traceroute, and there's more, but I just wanted to keep it at one page. So I see Tom at the mic, so please go ahead, Tom.
So obviously multi-path is a big issue. Most data centers are running multi-path.
You do or you do not see it as a big issue?
I do see it as an issue, right? Pairs traceroute kind of solves that issue, but the implementation of pairs traceroute are basically iterating over different IP packet attributes that are used for multipathing. Just no one's really implementing it. None of the hardware vendors, no one else implementing it. In your opinion, why do you think it hasn't taken over as the Traceroute version of it?
I don't know. I mean, I don't know that I could answer that question. Maybe the Traceroute that we've got by default is good enough for most people. Maybe, I don't know that much about Traceroute. I'm familiar with it, but could be licensing restrictions. It could be just cooperation. I have no idea. So that's a question I just can't answer, I'm afraid.
It's on this one.
Yep. Yes, sir.
John, thank you. I want to echo your remarks about the importance of Traceroute and network troubleshooting. I think it's something that we take for granted and really will tell you everything you need to know, I think. Specifically the forward and reverse path, reverse path being just as important as the forward path because of most routing being asymmetric now. And, that's the nature of that. DNS is important in Traceroute because it tells you the boundary relationships of different networks. I can see where I hand off to another network. And then I had one other point that I wanted to make, but I forget it now. But thank you. This
When
was a
you
great
remember, be
presentation.
sure to let me know. Tom, you had said repeat questions. Is that mic captured?
Yeah.
Okay, so I don't. Oh, yes, sir. I may have to repeat this
If you're
one.
using Linux, there's an MTR tool. I don't know
MTR,
whether
yes.
you're using it, but if you're not using MTR, I think that's such a much better traceroute.
There's a whole variety of tools that you can use. Gentleman spoke of MTR, for those of you who couldn't heard, is another measurement tool, and I believe that one will do a continuous stream of packets as well, and give you, help you figure out multipath kinds of stuff. So it's, yes, thank you for mentioning that. Of course, I'm sure there's many more things we could mention. I'd love to hear them, not necessarily because I didn't include them, but I may have forgotten about them. And if I ever do write such a book, it would be perhaps useful to include all of those good ideas. All right, well, thank you very much for your time and attention.